Today we're going to look at simplifying radicals. This is the last topic we'll have to cover before we can move on to chapter 1 in geometry. What a radical is, and some of you may be confused about that, so I'll go ahead and go over that with you. A radical is a square root, okay? So for instance, the square root of 5, that is a radical expression, okay? So we're going to talk about when radicals are simplified. So radicals are simplified when three things occur. There are no perfect squares in the radical. Of course, that is other than 1. 1 is a perfect square, but everything is divisible by 1, so that doesn't really count, not including 1. Okay, it is also considered simplified when it doesn't contain fractions under the radical. Okay, so for instance, this is simplified. That is a simplified radical. This is not. Okay, even though those are the two, even though those are the same, that's the same thing, this one is not all the way simplified because there is a fraction under the radical. Okay, so that is not simplified. This is. Okay, and then the last one is that there are no radicals in the denominator. They can be in the numerator, just not the denominator. Okay, so this is not okay. No radicals in the denominator at all. It's not simplified. Okay, so we're going to go ahead and dive in here and work on simplifying some radicals. So we have here the square root of 50. In order to simplify this, we need to look for perfect squares within 50. And so if you remember, as far as perfect squares go, we have 2 squared is 4, 3 squared is 9, 4 squared is 16, 5 squared is 25, and so on. I could keep going and going and going. Okay? You should know those perfect squares pretty much off the top of your head. Alright, so we want to find a perfect square within 50. Well, if we think about what 50 breaks into, probably the most common one you'll think of is either 5 and 10. Neither of those are perfect squares. It also splits into 2 and 25. So 25, as we can see over here, is a perfect square. Okay, the square root of 25 is 5. So the product property says that I can break this into two separate things, the square root of 2 and the square root of 25. And that is the same thing. So this becomes, the square root of 25 is 5, and then the square root of 2 is some irrational number, so we leave it under the radical. Okay? Let's go ahead and look at number 2 now. I'll draw a line so we don't get over into the wrong space. Alright, let's look at number 2. Number 2 is square root of 45. So if we look at 45, we know it's going to be divisible by 5, so if we do that, that's the square root of 9 times 5. 9 is a perfect square, so this becomes the square root of 9 times the square root of 5. The square root of 9 is 3 times the square root of 5. 5 is not a perfect square, so it has to stay under the radical. Okay, let's move on and look at some that are a little different. These we have separate radicals, and we want to combine them to make 1. And then we can simplify from there. Okay, so we combine this. This is the same as the square root. of 6 times 15. I can move them both under the radical, and it is okay. So 6 times 15, that becomes the square root of 90. So now we want to look for perfect squares within 90. Well, the most obvious one is it's going to be the square root of 9 times 10. 9 is a perfect square. The square root of 9 is 3, so we can go from there. So this becomes the square root of 9 times the square root of 10. The square root of 9 is 3 times the square root of 10. 10 does break into 2 and 5, but neither one of those are perfect squares. So we just leave it under the radical. All right, let's go ahead and look at number 2. So now on number 2, notice we have this 2 on the outside here. So what do we do with that? Well, in front of every radical, even if nothing shows up, there's always a 1 there. If there wasn't a 1, the radical wouldn't appear at all. Okay? So there's always at least a 1. So when this happens, we can multiply the outsides and then also multiply the insides together. But never multiply an outside with an inside. That'll mess you up. So if we look at the blue, we have 1 times 2 is 2 times the square root of 8 times 4. Okay, so this becomes 2 times the square root of 8 times 4, which is 32. And so now we're looking for perfect squares within this. 32 divided by 2 is 16. 16 is a perfect square. It's the biggest one we can get. So this becomes 2 times the square root of 16 times the square root of 2. So this becomes 2 times 4 times the square root of 2. 2 times 4 is 8 times the square root of 2. And we are done. Okay, there are several ways to do these, so if you did not do it the exact same way as I did, as long as you come out with 8 square root 2 and then 3 square root 10 over here, it is the right answer. Okay, so the last thing we want to look at is what do we do if there's variables in the mix? So what if I throw an x in there or a y in there or a z in there? How do I simplify that? Well, it's really the same as the number. You're looking for squares within those exponents. So let's look at the first one, x to the third. We know that this can break into x squared and x, correct? Because this x has an exponent of 1. 1 plus 2 is 3. Okay? So the square root of x squared is just x, and so there's an x left inside. I know I went through that really quickly, so we'll go through the other one a lot slower. Let me show you another option for this. We can also look for pairs of 2 when we have square roots. So for instance here, you know that x cubed is the same thing as x times x times x. Okay? There is one pair of 2's in x cubed, so we know that 1x comes out, 1x stays under the radical. Alright, so since we have one pair of x's, 1 comes out, and then we had this 1 left over, so it stays in. Now let's look at y to the 5th. You know that y to the 5th breaks into y 5 times. 1, 2, 3, 4, 5. So we're looking for pairs of 2. So there is 1, 2 pairs of 2. So 2 y's come to the outside. Okay? And then we have this 1 y left over, so it stays in. Alright, the last one, let's look at the z's. Z to the 6th, that is the same thing as z 6 times. Okay, so now we also have pairs of 2. We have 1, 2, 3 pairs of 2. And so 3 z's come out. And for that one, no z's are left inside. We use them all. So now we can go ahead and multiply everything outside. So we have 1x, y times y is y squared, and z times z times z is z cubed. And then on the inside, we have the square root of x times y. And so that would be your final answer with that one. All right, the last one we're going to look at is number 3. This one has some variables and some numbers in the mix. So when we look at this one, we're going to look at 18. What can we break into where it will have a perfect square? So 18 breaks into 9 times 2, and 9 is a perfect square. And then we're going to look at a to the 5th. Well, that's a 5 times, and that has 2 pairs of a, and then 1 left over. So now we're going to look at our b's. There are 4 of those, which is enough for 2 pairs. And then last, we're going to look at our c's. And this is getting really long, but there are 7 of those. Okay, and 7 makes 1, 2, 3 pairs with 1 left over. Okay, and we also had 1a left over. So now let's look at what comes out. Alright, the square root of 9 is 3, so a 3 comes out. The 2 stays in, because the square root of 2 is some decimal. There are 2 pairs of a's, so 2 a's come out. There are 2 pairs of b's, so 2 b's come out. And there are 3 pairs of c's, so 3 c's come out. And then let's look at what's left in. There's an a left in here, and then there's a c left in here. Okay? And so now if we multiply the outsides, that's 3a squared, b squared, c cubed. And then 2ac is left inside. Okay, so that would be your final answer for that one. All right. Okay, so now what I want you to do is try the last 3 problems here. Pause the video. When you unpause it, I'll have the answers up. Okay, so here were the final answers for these 3 problems. You can see all of my work. If you have any issues with this, we'll go over it tomorrow in class. I'm also available before school, so don't forget that. See you in class.